All right, so now we are going to do two really long and very important examples. Now, I sent you an email about this morning. Well, when you watch this, it's not going to be this morning, but anyway, I sent you an email about this. I don't want you to just sit here and scribble everything down that I'm doing, because then you're not going to really learn a lot. You're not going to understand a lot of it. So the examples I'm going to do, I already sent you the solutions in gory detail. So in my email that I sent this morning, I instructed you please to print out the solutions. And so when I'm doing the work, you can kind of just follow along with me and just concentrate on understanding, all right? Just understanding, because this is what you're going to be doing this chapter and next chapter. Okay, so I hope you have the solutions nearby when we go through all this. Okay? All right, so this is example 2, right? Okay, so here is just some made-up thing, right? So this is the probability density, right? And notice the units, centimeters and -1, because probability density is probability divided by a length. So it has to have units of a length to -1. So here's probability density, centimeters -1. Here's x, centimeters. So this area, is going to have no units. Okay, cool. And we also have the probability density is equal to the wave function squared. All right, number 1. Draw the dot pattern. Well, okay, just draw the dot pattern, all right? So draw the dot pattern just to get it in your head. I didn't do it, so lazy, right? Okay, the dot pattern, you're just going to have a ton of dots here, less. Okay, that's really the dot pattern. I don't know about you, it drives me crazy doing all that, but that's okay. So that's the dot pattern. Number 2, we forgot to figure out A. Well, nope, we know how to do that. Okay, so again, this is 0 to infinity, that's 0 to infinity, so the probability that the particle is in here is equal to 1. So we just got to figure out A to make this area equal to 1. Not a big deal. All right, let's do it. So the area has to be 1, that's half base times height. Okay? So that 2 kills that 4, and we get 2. So therefore, A equals 1/2 centimeters to the -1. All right? All right, so A is 0.5 centimeters to the -1 power. Great. All right, next thing. Determine how many of 1,000,000 photons land in a tiny region located, or interval, located at 1 centimeter. Now there's two kinds of problems we're going to see today. This is the one where the photons are landing in a really narrow region. Okay? The next one we're going to do is where they're landing over a large region. And we're going to handle these completely differently. Okay? So, but come on, we've already talked about this, right? This is expected value, yeah? Okay, so how many out of 1,000,000 photons land in a tiny region, delta x, located at 1 centimeter? Okay, so that's this. That's all it is, right? Not a big deal. Okay, so you'll see, I'm not lying. Okay, so, all right, so it's the probability density times the width. Piece of cake! Not really. So first we got to know what P of x is at x equals 1. Well, man, too bad it's not graph paper. We could just read it right off, right? Ugh. Well, it's not graph paper. We can't read it off. What a bummer. So how are we going to figure it out? We're going to find the equation of this line, and then we're going to put in x equals 1 to figure out what the P of x is. Sorry. All right, so that's what we got to do. We got to find the equation of this line so we can figure out what this is right there. No problem. We can do it. So, you know, y equals mx plus b, right? Okay, but what we have p of x equals the slope times x, you know, plus the there. I should have wrote it like that, right? This is the slope, that's the intercept, okay? So let's do the slope. So the slope, which is m, you know, is the, you know, the rise over the run, or delta y over delta x, whatever you want to call it, right? Okay, so it's that minus that, right? So it's a, okay, so it's 1/2 in 0.5. 0.5 centimeters negative 1 minus 0. And then the change in x. So this is 0. This point is 0, 1/2. This point is 4, 0. So it's 0. Oh, sorry. And this is 0 centimeters minus 4 centimeters. Okay? And what's 1/2 divided by 4? It's 1/8, but we have a minus sign. So it's minus 1/8. Now look at the, let me write this as 1/2. Maybe that'd be better. Okay? 1/2 divided by 4 is 1/8. Now look at the units. This is centimeter negative 1. This is centimeter. What's a centimeter? So it's like a 1 over centimeter divided by a centimeter over 1, right? Right? This is centimeter minus 1. This is centimeter. What's that? Centimeters negative 2. Centimeters negative 2. Okay, so that's the slope. And you got to do these units. I mean, you'll see we're going to have really weird units when we start normalizing things. Okay, what's the y-intercept? What's the y-intercept? Well, the y-intercept is nice. It's just a, right? It's just 1/2, right? So the y-intercept is 1/2 centimeters negative 1. It's just a. Yeah, we found that right there. Okay, good. So that means that the equation of the line, so we have p x, that's like the y, equals the slope minus 1/8 centimeter negative 2 times x plus intercept plus 1/2 centimeter negative 1. Okay? That's what it is. It's pretty weird. All right? Now what we want to know is we want to know the probability density at x equals 1, right? Right? So you put it in. So probability density at 1 centimeter equals 1/8 centimeter negative 2 times 1 centimeter plus 1/2 centimeter negative 1. Okay, well what's that times that? It's still it's negative 1/8, but we have centimeter minus 2 times centimeter, which is centimeter minus 1. So we have minus 1/8 centimeter minus 1 plus 1/2 centimeter minus 1. Well, 1/2 is the same thing as 4/8, right? So minus 1/8 plus 4/8 is 3/8. So we have 3/8 centimeter negative 1. Okay? So that means that the probability density at 1 centimeter equals 3/8 inverse centimeters. Awesome. Okay? And again, this is probability density, so it has to be probability divided by a distance, which we have. Okay, so P of x is what I just said, 3/8 inverse centimeters. Now, the width, what's the width? What's this delta x? Right here, 0.001 centimeter. Okay? And so now we're going to use this equation. All right? So, oh golly. Okay? So now, the probability that the thing is in a width 0.0, how many zeros? 2 zeros. 1 centimeter at x equals 1 centimeter is equal to p at 1 centimeter, right? P at 1 centimeter times that width, 0.001 centimeter. Oh, sorry. Okay, so all right. So this is equal to probability density at 1 centimeter, 3/8 centimeter negative 1 times our width, right? This is the 3/8. That's our width, 0.001 centimeter. And I promise, now look at the units. Inverse centimeters kills centimeters, right? Because it's a probability, you know, right? It's a probability, no units. So I promise you when you multiply that by that, you get, oh gosh, 0.123375. Okay? All right, so that's the probability, right? That is the probability. Awesome. Now, what we want to know is if you throw 1,000,000 photons, how many are you going to get there? Well, this is the probability of 1 photon, right? Just probability. Now we want to get the expected value, right? So n expected equals n total times the probability, right? All right? And so that's going to be 10 to the 6th times 0.000375. And that comes out to be, guess what? 375 photons. Okay, you're going to do problems like this on the homework and on the exams. So you better know how to do it, right? So please make sure you know how to do it. Oh, I guess we're not done yet. There's another section. All right, so this, again, so this problem, you know, we wanted to know how many photons land within a really, really narrow band, right? And so we had to use this formula, okay? This formula. Now, we got the next part of this question, I think. Yeah, okay, now number 4, oh gee. Number 4 is different. I mean, it sounds similar, but it's different. This one says, determine how many out of 1,000,000 photons land in the wide interval between 2 and 4 centimeters. Okay? So it's no longer this little narrow band. It's this big, big interval. Oh my gosh. So how are we going to do that? Well, hold on. Okay. All right, so, I mean, you know, we could just be lazy, right? Right? I mean, you know, this is a half, 2 and 4. Just by similar triangles, you know this is a fourth, right? Right? And then you can just calculate the area of this triangle. So let's just do it. So it's 1/2. The base is 2 centimeters. The height is a fourth inverse centimeters. So what's that? That's a fourth, right? 25%. Right? So that's the probability. There, we just did it. All right? All right, so the probability that it lands in here is 25%. Makes sense, come on. This triangle is the same as that triangle. Split this thing up. You have a triangle there and a triangle there. So you have 1, 2, 3, 4 triangles. This is a fourth. So that's the answer, but, well, it's not the answer, but that's the probability. But we don't want to do it that way. We want to do it the long way, okay? Well, do we really? No. Yeah, we do. All right, so let's do it the long way. Of course, I erased everything I needed, but that's all right. Okay, so let's say it wasn't so nice. Let's say it wasn't, you know, let's say it was some other point up here. So we have to use the equation of the line again. Okay. I had earlier written this. For the equation of the line, it's minus 1/8 centimeter negative 2 times x plus 1/2 centimeter negative 1. Right? That was the equation of this straight line. So we want to find out what the probability density here is at x equals 2. Okay, we do it. So probability at x equals 2 centimeters equals minus 1/8 centimeter negative 2 centimeters, 2 centimeters plus 1/2 centimeter negative 1. Okay, an eighth times 2 is a fourth. So we get minus 1/4 centimeter negative 2 times centimeter 1 is centimeter negative 1 plus 1/2 centimeter negative 1. That's 3/4, right? So it's, it's 1/4. It's negative, right? So, right? What did I just say? Yeah. So it's negative 1/4. What? I mean, it's positive 1/4. What are you talking about? Positive 1/4. 1/4 centimeter negative 1. Sorry. Okay, and so we sort of already knew that from just similar triangles. But now we did it the long way, right? Minus 1/4 plus 2/4 is 1/4. Okay, that's cool. All right, so we know that what this is now. So we don't have to do this equation like we did the last time, We don't have to do this because this was great if this was a tiny narrow thing, but now we have this wide thing, right? So, so the probability is just this area. So the probability is 1/2 base 2 centimeters times the height 1/4 inverse centimeters. And that's, what is that? It's a fourth, right? It's a fourth. No kidding! I mean, we kind of knew that already, all right? So then, how many of a million photons are going to land there? It's just it's a million photons times a fourth. So it's 250,000, right? So n expected is n times the probability. So it's a million times 0.25, so it's 250,000 photons. There you go. All right, so we did two different ones, right? Two different types of examples. We did one with narrow, or then we did one with wide. Okay, oh gee, do I want to do this? Yep, I gotta do this. All right, we're gonna do another one. This might take a while. Actually, let's cut. Let's cut now, and then we'll